At Mach 1, you don't have time for a garbage collector. In most programs, a bug is just an inconvenience. A crash means you restart the app. What happens when failure isn't an option? When one bad line can be a catastrophe. And this is what stands in your way. It's not about what's in the code, it's about quantifying what you take out. Today we're going to learn how to program like a fighter pilot. June 4th, 1996. It's a warm morning in French Guiana. The weather was acceptable. Hundreds in the crowd stood to watch the launch of Europe's newest rocket, the Ariane 5. 9:33 a.m. local time. The solid boosters fired. For 36 seconds, the flight was perfect. And then, a single, unhandled exception was thrown deep inside the flight control software. A 64-bit float of horizontal bias converted to a 16-bit integer. The language did exactly what it was allowed to do. It triggered an error the system couldn't handle. $500 million destroyed in an instant. In this particular situation, an exception was detected, but it wasn't properly handled. So when the designers of the F-35 came around, they decided that they weren't going to make any of those same kinds of mistakes. JSF C++ standard section fault handling, AV Rule 208 states, exceptions shall not be used. This is a perfect kind of example of remove before flight. By cutting out certain features from a target language, we can actually build something that's safer. But first we have to ask ourselves, how did we get to this point? What do I mean by program like a fighter pilot? Why does it matter? And why do I have a GameCube in front of me? It'll make sense later. I got my, remove before flight earrings too. These look familiar? You probably should remove these earrings before flight. I can't imagine it's just gonna be like slapping you in the face as you're trying to fly a plane. Now this isn't just a history video because I think that the best way to possibly learn is to get your hands directly on the code itself. So I'm gonna be doing a demonstration in C++ following the strict JSF standard connected to my F-35 inside of a flight simulator. But first I wanna talk about some really pivotal moments that made C++ even possible inside of aerospace. And it's actually harder than you think. I want to talk about the language wars that were fought inside of the Pentagon, and that's not as scary as it sounds. Now fundamentally, modern aerospace, particularly military aircraft, are a lot more about software than they really are about hardware, and probably a lot of people are going to disagree with me on that, but you gotta hear me out. It's not really like flying a plane that happens to have a computer on it. It's much more like you're flying a computer that happens to also be a plane. Back in the early 70s, military fighters like the F-4 Phantom over here basically had no software. And you don't have to take my word for that because the DoD explicitly states that. The bombing computer on the F-4 was pretty much just a box of gears and cams, kind of like a precision watch. And then the code, if you want to call it code, was pretty much just the shape of the metal cams. This all started to change, however, with a top-secret Navy air superiority project, the VFX. Although you probably know it as the F-14 Tomcat. Now, not a lot of people know this, but the first microprocessor was not created by Intel. I know what you're thinking, but Lori, every textbook in the world lists the Intel 4004 as the world's first microprocessor. But that is because it was actually a secret. Garrett I Research created a microprocessor for the F-14 years before Intel did, and it was significantly faster. The main reason was the F-14's swing wing design, where manual pilot control would have been way too much for optimal performance. Wow, I hear a plane. Oh my goodness. Especially during high-G maneuvers. This information wasn't declassified until 1998, however, since the Navy wanted to keep it from the Soviets. It didn't really have lines of code in the classic way that we think of it today, since it was physically burned microcode that processed polynomial equations. About 2,500 lines of code, and thus began the first real software on a plane. The early software era was a mess. The US Army, Air Force, and Navy all had completely different coding standards, and I'm sure you haven't heard of any of them. The Air Force liked Jovial, which stands for Joule's own version of the International Algorithmic Language, and no, I'm not making that up. It was kind of like the military grandchild of Algol. Of course, the Navy had to be different because jovial was an Air Force language for Air Force problems, and thus the F-18 became the poster child for the Navy's own language, CMS-2. Two different languages, two different hardware architectures, and zero compatibility. Now, the military saw this kind of writing on the wall that the amount of onboard flight software was basically increasing exponentially, and to kind of put that in perspective for you from the original era over to modern era of code, you start out with like 125,000 lines of code over on the F-16A, and then you progress over to 1 million lines of code on the B-1, and then if you come to the actual modern era of aerospace computing, you come to the F-35 with 9 million lines of code on board, which is just like a crazy trajectory. You guys want to see exponential curve demonstration? It's like that. That's like the lines of code. Now, the problem was that the code was becoming kind of like this massive jungle to audit. At one point, they reported that there were like over 450 different programming languages being used, and none of them had their own like proper standard for them. So what they decided to do is they decided to come up with a new high-level language that would replace all of these other different random languages actively being used, and that high-level language became Ada. So the Department of Defense really, really wanted people to use Ada, so much so that they made this kind of mandate where if you did not want to use Ada in your task, you had to physically prove that it was not possible to be used. So that's how much they wanted people to use it. And it's kind of like, if you're not going to use Ada inside of your project, then you're not going to get the contract. Now, many of you might be familiar with coding in C++ every day, but you might not be as familiar with coding in Ada every day, or even possibly ever. Ada is actually really good for safety critical applications, and of course this is vital inside of aerospace, and this is going to kind of start sounding very familiar for you. Going back over to our history portion, that Ada mandate lasted about 15 years until some problems started kind of making an appearance. So basically in the 90s in aerospace, pretty much everything was run on Ada, but simultaneously you have all of this cool stuff happening. You've got the internet, you've got Windows 95, and pretty much every good game is going to be running on C++. So that's getting pretty boring to still be stuck inside of Ada. Not only that, but say you're a student in the 90s and you want to get some kind of high-paying software job, you're not going to be learning Ada. And I'm about to blow your mind here, but compilers used to cost money. Like a lot of money. So back in the day, Ada compilers cost like literally thousands of dollars. So you might be thinking, what are you, crazy? Compilers cost money? We get all that stuff for free these days. So it kind of makes sense that students back in the day jumped on board that C++ and GCC bandwagon of the free software express. I like that. But that started to become kind of a problem when you enter the days of Lockheed Martin working on the F-35 project, because Lockheed Martin knew this was going to be an extremely software-heavy aircraft, and it was going to have a lot of different complex concepts and calculations on board, like sensor fusion, for example. In order to kind of start remediating all of these potential problems, they decided they were going to achieve the impossible. They were going to convince the Department of Defense to let them use C++ instead of Ada. And I honestly have a lot of respect for the person who decided initially to make this kind of proposal, because they were either absolutely crazy or they were just so determined they were going to make this happen. And also would have been like to have been a fly on the wall during the Pentagon meeting for this, because it's basically like the contractors coming over here saying, please let us break the law and do it with your approval. Please let us use this new unsafe language and ignore every single other software mandate you've made up until this point. But they didn't also go in completely unprepared, because they decided they weren't just going to use raw, plain C++, they had a plan to kind of tame the language. Now, who better to ask for advice at coming up with this kind of C++ cherry-picking plan than Bjarne Stroustrup himself, the creator of C++. And kind of fun fact for everybody, I actually have met him in real life at a conference, and I'm proud because I did ask him a question. I asked him about C++ 26 reflection capabilities. Spoiler alert, completely different, and he really does not believe in the Java style of reflection, but yeah. Anyway, going back over to our history, the details are a little bit fuzzy, but Bjarne himself did actually admit that he did have a hand in the formulation of the JSF rules, so he said you had to consider him biased about the topic. Going back over to our remove before flight concept. You remember me talking about this? Well, this is exactly how the Joint Strike Fighter, or F-35 C++ standardization actually works. By kind of surgically removing specific portions of an otherwise extremely powerful language like C++, developers can create code that's much more likely to get mission or safety certified without also being shackled to a prehistoric language like Ada. Kind of the craziest part is that you can read the JSF standard completely publicly online if you want to see how the F-35 is actually programmed, at least from a stylistic perspective. Now the key for this openness kind of somewhat lies in the name itself, Joint Strike Fighter, and actually it wasn't just Lockheed that was working on this aircraft. It was Lockheed, it was a ton of other defense contractors, it was a ton of governments, it was even a ton of different countries all working kind of in tandem together on this aircraft, which is pretty cool, like as a group effort. And not only that, but if you have the JSF standard just publicly online, you too theoretically could contribute compliant code to a billion-dollar aircraft project. Now I think the best way to learn is just to get out there and start writing some C++ code while following the JSF standard. And it might kind of sound crazy, but side note here, my actual job used to be writing C++ for aerospace systems and putting on demonstrations for the Air Force, so I did live in this world for kind of a decent amount of time. And for today's demonstration, it's going to be a heavily simplified version, and I'm mostly going to be focusing on the quirks of C++ while following the JSF standard. Now for the most fun part of this video, for me, I'm gonna fly a flight simulator. So I'm gonna be using X-Plane 12, which is a really popular flight simulator, and it is actually used in the industry pretty decently often. It's really good for software integration testing or just general flight demonstrations. And I'm going to start a new flight over here, and I'm gonna use the F-35B, released by AOA Simulations pretty recently, and it's pretty accurate and cool looking. So I'm gonna start my flight. Here we go. While this is loading, this is my multifunction display that I built over here, or my MFD, and this is F16 style, and you can see it's got all of this data available. This is connecting to X-Plane itself. So X-Plane very recently made this web API that you can subscribe to, so you're constantly listening to that live flight data that's being published over that web API. Now the front-end portion of this UI is just in Python, but the back-end portion of it is in the C++ code, and that's where we're gonna be demonstrating the JSF standard at the moment. You can see I've got my main display here connected live to the aircraft from X-Plane, and I can go over, I've got like my position data, got my wind data, envelope data, got questionable buttons. I've actually got some weird multi-threading problems happening in Python at the moment connecting to my buttons. It's kind of a process to get this to work. I've also got my navigation data, so all of this back-end calculation portion needs to be done in optimized, JSF-safe C++ code. And I gotta have my cool Top Gun glasses if I'm gonna fly. They only slightly affect my visibility for looking at a computer screen. By slightly, I mean a lot. Alright, so keep in mind the aircraft data is live getting updated on my MFD over here. So let's take off. I actually cannot see. It's fine. I can still fly. That's what you want to hear your pilot say right before they take off. Yeah, guys, I can't see. Here we go. And my location data is getting updated. It was such a smooth takeoff. Alright, let me see if I can show you. If I can multitask and find. Yep, here's my position data. And remember, it's reading from that web API from X-Plane, so it's actually getting updated, both at the same time. Starting to understand the concept of pilot load over here. I'm sure this is the same. Can I do a barrel roll? Oh, that's so easy. I'm such a great pilot at this. Wow. Okay. Okay, where's the up part of my plane? I can't actually see. Okay, we're good. Here we go. Nope, I need pull up. Okay. I wonder if I could dip my wing in the water just like a little bit. Nope. Okay. No, I cannot. What's that quote from Top Gun? When you're up there, if you think, you die. Apparently I was thinking too hard. We're gonna go with that. Now let's get on to the most important part of this, which is going to be the C++ code. Not as exciting as X-Plane, but actually no, it's more exciting. I take that back. So I have my X-Plane flight data plugin here, and this I'm going to link to in the description of this video. This is available on GitHub, and this contains all of the important code that's executing on my MFD over here. And if I go through this repository, I have my aircraft mfd.py. Not super interesting, it's really just the GUI portion of this. But if we go on to our compliant and non-compliant folders, that's where the interesting C++ code actually lives. And of course, compliant and non-compliant relates to the JSF standard. I'm going to go into my non-compliant folder and let's just see kind of what data we're calculating here. This is my density altitude calculator.cpp. I've also got flight data, turn calculator, VNAV data, wind calculator, all of these important calculations that are either mission critical or safety critical are living inside of C++ code. So this C++ code needs to be 100% reliable 100% of the time, and that's why we have to follow such strict standards. So keep in mind our remove before flight tag, because this is going to be a very important concept. Let's go on to the flight calculator. This file is really really long. I highly encourage you to take a look at some of the calculations. They're very interesting and very math heavy, kind of fun. I think I had too much fun writing, oh my gosh, all of this code. We have something related to memory allocation, so see if you can find the potential issue here inside of the code, like what could be going wrong if we hit this code and it's not following the JSF standard. There's a second one inside of here. This one's probably pretty obvious, but look at this function. This is a very unsafe function to have on a plane. Now let's take a peek at the actual JSF, or Joint Strike Fighter standard for C++, and this is extremely long. Like, it goes on for forever. If I go over to the table of contents here, you can see how many topics it actually covers, and these range from things about stylistic guidelines as well as kind of safety guidelines, particularly related to, I would say, 3 main topics. Now, if you want to program like a fighter pilot, or rather kind of program for a fighter pilot, probably, these 3 things that you need to keep in mind are related to memory allocation, exceptions, and recursion. And there are a lot more rules as well, but these are the 3 things that I'm going to be focusing on today. And in the end, the safety aspect of it really comes down to removing things from a language rather than adding things to a language so that you can have extremely predictable behavior. Now, side note, today I've been running on my Mac for simplicity, but what if I told you the real thing was a lot closer to this? I know you've been waiting for the whole time for me to come back to the GameCube, probably on the edge of your seat. But the earlier Block F-35s used mission computers based on Motorola G4 PowerPC processors. And this is all public information. You can actually go back to the Aviation Today articles from like 2003 and see this being discussed. Now obviously it's been ruggedized, it has special vector extensions, and a lot of other cool stuff added on top, but kind of the core instruction set architecture is very similar. And that's just a fun fact. If you want to get really technical about it though, technically the GameCube is a generation old, and so kind of an even better match would be something like this. But I'm not going to compile on this just to prove a point. Or am I? No. Alright, now back over to our simulation, our C++ and our JSF standard. We're going to have to break out this remove before flight tag here because we are going to need it for the code that is actively executing right here, right now, on our aircraft. So picture this, you're a C++ contractor and you've written some C++ code. Good practice, but it's not been JSF-ified. JSF-ified. It's kind of fun to say. So, as a pilot right now, I'm actively flying my aircraft and I'm going through all of my data that's available to me. Going through, numbers are looking pretty good. Oh no, we've encountered a C++ exception, and instead of handling it properly, my computer has just completely given up and we have totally crashed. And I'll probably crash my plane very shortly. So what just happened inside of our program, and how do we ever prevent this from happening on an aircraft again? Now, the first thing that might surprise you is AV Rule 208 from the JSF standard, which states that exceptions shall not be used, which you might be thinking, why? That seems kind of extreme. But the core problem here is that they generate kind of an unpredictable flow of control. So if you go back and you think of that Ariane 5 incident that we talked about previously, the problem wasn't that the value overflowed. The problem is that it generated an unhandled exception that nobody had planned for. And that is just the worst possible thing that can happen inside of safety critical code. Just to be clear, Bjarne himself is actually a very big supporter of modern day C++ exception handling, and exceptions are fairly cheap. So why do we not have them inside of the JSF standard? And the answer to this is mostly just due to maturity at the time. And I think the best way to describe this is to quote Bjarne himself. And he said, JSF++ is for hard, real-time, and safety-critical applications, flight control software. If a computation takes too long, somebody may die. And for that reason, we have to guarantee response times, and we can't, with the current level of tool support, do that for exceptions. So it just goes back to maturity, like I said. And the funny thing is, the JSF standard actually simulates exceptions, kind of getting ready for a date when the tooling is capable of handling it. If we go over to our code and we want to fix our C++ code that generated the fatal exception during our flight scenario, let's take a look at what that looks like. So if I go over to my density altitude calculations, this is where the unhandled exception was thrown. So now taking a look at the code, this is my non-compliant JSF version. You see we've still got our remove before flight tag, very important. But what is actually happening inside of the code? If you're following AV Rule 208 for no exception handling, you can see we've got a lot of keywords that are simply not allowed inside of the JSF standard. All of this try and catch block over here with our stood exception, as well as our throw statement over here, none of these are actually allowed. Now, what does it look like if we go through and fix it? Let's go over to our compliant version, and how do we handle exceptions in a fully JSF compliant manner? Well, what we're going to do here is we're using return codes instead. So if you're throwing an exception, then that has to be handled by a proper exception handler. But if you're using return codes instead, you can see I have this code that is set to different values based off of what might happen inside of my density altitude calculations. With this return code though, that is leaving the handling portion in the hands of the calling function. So now the calling function can take in that return code that is being passed over and decide what it wants to do based off of this return code, instead of just completely failing and breaking the entire program. And now we're back on board with our completely flight safe software. Here we are, and we're flying along, and now we can take a look at our MFD, and I can cycle through all of these values, go over to my density altitude calculations, and you can see we're not generating any unhandled exceptions anymore. So if we have that value that gets returned and it somehow misses its calculation time, or we get like a completely empty value, it doesn't matter because we're returning that error code instead of just generating an exception and completely crashing our program. Not like I'm about to do with my plane right now. Okay. Talking and flying is very hard at the same time. The second big area that we need to address inside of our flight code is AV Rule 119, which states that any function is not allowed to either directly or indirectly invoke itself. AKA, you can't use recursion. And you might be thinking, oh, that kind of stinks, because I personally like recursion a lot. I think it's really cool. But the main problem with recursion is that it basically exposes you to the possibility of having stack overflows inside of your code. Now, when you're calling a function, you're actually setting up a new stack frame for that new function. So with recursion, you're setting up frame after frame after frame, and all of these new function invocations are getting added onto the stack. And the problem is, with recursion, you often don't know the upper bound of the maximum depth that you're going to recurse inside of your function. And that's a big problem in these safety critical applications where you need to know the maximum upper bound of how much memory you're going to use. Now let's go through and let's fix our recursive calls inside of our actual C++ program and make this JSF compliant. So I'm going to go over to my flight calculator, and I am computing the binomial coefficient inside of my flight calculation for computing different alternative airports during my flight plan. And if we want to take a look at the recursive portion of this, I have my binomial coefficient function declaration up here, and inside of our definition you can see we're invoking ourself 2 different times. We have the binomial coefficient invocation for n-1, k-1, plus another call invoking itself for binomial coefficient n-1k. So this is like doubly not following the standard. But the problem is that for each of these different recursive calls inside of this function, we don't know like the maximum depth, so this kind of opens us up to the possibility of running out of memory inside of the program. So let's go over to our JSF compliant version and see how we fix this. And I did mention that iterative approaches are usually not as pretty, and I stand by this because you can see this code a little bit longer. I don't know, feels kind of lame. Not as nice as the recursive calls. But you can see we are JSF compliant now because we have our binomial coefficient function definition and we have no invocations of itself inside of the function. Now we fixed our problems with exception handling, we've also fixed our problems with recursion. Now it's time to move on to the last and probably the most important thing that we need to remove before flight to be compliant with our JSF standard, and this is related to memory allocation. Now AV Rule 206 states that both memory allocation and memory deallocation shall not occur after initialization. And basically this means that you can't go through and you can't be allocating any memory while your program is actively executing. And this is there for a couple reasons, mostly because it introduces some unpredictability in your code. You don't know how long it's going to take the memory manager to find the memory that's available for your newly allocated data. Also, you don't even know if there is enough memory that's available for you to allocate this brand new memory. The issue is that as you're allocating memory, you're allocating it onto the heap, and that can cause something called fragmentation. So as you're allocating more and more data, you're kind of fragmenting the heap into these tiny unusable chunks of data that you can't use when you're allocating something new and large that's not going to fit into that data. Now let's go over to our C++ code and let's see how we can fix our non-compliant memory allocation problems. So right now I have my history of my indicated airspeed, or my IAS data right here. This is being used to calculate gust. But the problem is this particular line right here. Now what this is doing is this is making a unique pointer and then returning this to our history buffer variable, but the problem is this specific portion. This is actually dynamically allocating new memory onto the heap, like I mentioned, which is a big problem when following the JSF standard. So how do we go through and fix this? Well, let's go over to our compliant version of our C++ code. And the biggest fix, there are multiple different fixes that you can do, but what I decided to do is I decided to hardcode a maximum data size for our particular IAS history array. So you can see we have this max IAS history, and this is being used in our initialization of our data. That means we can use all of the available indices inside of our data array here, but we already pre-know the exact maximum size possible, so we never have to dynamically allocate anything. And then we can still perform our calculations inside of this, but we've completely fixed our dynamic unknowns. Now I want to give you a bonus real quick, and that's AV Rule 3, which states that the cyclomatic complexity of a function shall not be greater than 20. And what does that mean? Well, the cyclomatic complexity is basically how many decision paths there are inside of a function. So an if statement, a while loop, a for loop, even Boolean operations like and or switch statements all count as points towards the overall cyclomatic complexity of the function. To go to a hands-on example where I think it makes more sense, let's take a look at our iterative version of our binomial coefficient function. Now the function declaration counts as 1 towards our cyclomatic complexity, and now we have this if statement right here. So if, that counts as another +1 towards our cyclomatic complexity, another if, that also counts as another point. Also, this or statement counts towards our cyclomatic complexity. Moving on, we have a couple more inside of here. Each of these are adding points towards our overall cyclomatic complexity, as well as our for loop down here. Now, that means that each of these points that we're counting towards must be below 20 for the entire function. Now I'm able to fly my aircraft without any problems or any potential problems that might happen on my MFD over here with any of my plugins. And I can fly with a peaceful mind. I'm feeling the need for speed. This is too much fun. Wish I had missiles on here. Whee! Okay, woo! Pull up! Emergency! I saved that. I really, really want to dip my wing into the water. I can do this. I think I just need to slow down. I can so do this. We're gonna just dip our wing. Okay, hold on. Whoop! There was a wall. Oh no, that's a highway. We do not dip our wings into the highway. Now the coolest thing is that the principles of the F-35 C++ standard didn't just end with that standard itself, and you can kind of see the DNA of it spread through a lot of different fields and a lot of different other standards. For example, another one is the NASA standard, which is called F-Prime, and that's their own standard for their own flight software. And this was also made publicly available back in 2017. If you take a look at it, it might look a little bit familiar because you've got no memory allocation, you've got no exception handling, you also have no recursion. So this is kind of like the sister standard to the JSF standard. This kind of idea of the coding standard for C++ isn't really just specific to aerospace. You also have it in a lot of other industries, like the automotive industry, for example. You have things like MISRA and AUTOSAR, which stands for Automotive Open System Architecture, and this actually references JSF by name, saying it's one of the influences for its C++14 standard. Now, being part of a much more modern version of C++, it has some benefits and some extra abilities that the old JSF standard didn't have, like smart pointers, for example, are allowed inside of AUTOSAR. If you think about it, cars are kind of like computers on wheels, especially with all of like the modern enhancements to vehicles and stuff. So all of these companies are dependent on AUTOSAR. You have BMW, Ford, Toyota, basically all of the major companies. And like funniest thing to think about is that all of this language safety, since it references like the JSF standard, is basically dependent upon a decision that was made by the Pentagon like literally decades ago. So here we are, we've got our code running, our systems are green, our code is following the JSF C++ standard. We have successfully coded like a fighter pilot. But here's the big question: should you follow the JSF standard inside of your C++ code? Here's a twist, and it comes from Bjarne Stroustrup, the creator of C++ himself. Now, even though he was part of the committee to formulate the JSF standard, he'd tell you that today you should be using C++ core guidelines. And he's got a point, because modern day C++ has continued to evolve and grow and not just stay the same for the last 20 years. So even though the JSF standard was a really great engineering feat for its time, you should be using newer, modern, safe C++. Despite this, you should definitely still take a look at the JSF standard, just because it's such an important and interesting part of history, and it managed to turn a really complex language like C++ into something predictable that's safe for critical infrastructure. And it's not always just about being the smartest programmer in the room, it's about having the discipline of knowing what aspects to remove before flight. Lori wired out.